Welcome to this lesson on electric field. Today, we're going to explore one of the most fundamental concepts in electricity, the force field that exists around charged particles. An electric field is an invisible region of influence that surrounds every charged object, and understanding it is crucial for grasping how electricity works at a fundamental level. So, what exactly is an electric field? Simply put, an electric field is a region of space around a charged particle or object. In this region, any other charged particle would experience an electric force. Think of it like this. When you place a charge somewhere in space, it creates an invisible sphere of influence around itself. Any other charge that enters this sphere will feel a push or a pull. This sphere of influence is what we call the electric field. Electric fields have several important characteristics. First, they exist everywhere around a charged object, extending outward in all directions. Second, an electric field is a vector quantity, which means it has both a magnitude or strength and a specific direction. Third, the strength of an electric field decreases as you move farther away from the source charge. And finally, even though electric fields are invisible to the naked eye, they have very real and measurable effects on any charges placed within them. The electric field can be calculated using a simple formula. E equals F divided by Q here. E represents the electric field strength. F is the electric force experienced by a charge in the field, and Q is the magnitude of the test charge we place in the field. This formula tells us that the electric field strength is simply the force per unit charge. In other words, it's the amount of force that would be exerted on 1 coulomb of charge at that location. Electric field strength is measured in specific units. The standard SI unit is newtons per coulomb, abbreviated as N/C. This makes sense because we're dividing force in newtons by charge in coulombs. However, there's an alternate unit that's equally valid. Volts per meter, or V/M. These two units are completely equivalent. You can use either one depending on the context of your problem. When dealing with a point charge, we can calculate the electric field using another formula. E equals kq divided by r squared. In this equation, k is Coulomb's constant, which has a value of approximately 9 times 10 to the 9th Newton meter squared per coulomb squared. Q represents the source charge creating the field, and r is the distance from that source charge to the point where we're measuring the field. Notice that the field strength is inversely proportional to the square of the distance, which means as you double the distance, the field becomes 4 times weaker. The direction of an electric field depends on the sign of the charge creating it. For a positive charge, the electric field lines point radially outward in all directions, away from the charge. This represents the direction a positive test charge would be pushed if placed in the field. For a negative charge, the situation is reversed. The electric field lines point radially inward, toward the charge. This represents the direction a positive test charge would be pulled. This convention is important to remember when analyzing electric field problems. Let's review the key takeaways from this lesson. First, an electric field is a force field that exists around all charged objects. Second, it's measured in newtons per coulomb, or equivalently, volts per meter. Third, the field strength follows the inverse square law with distance, meaning it gets weaker as you move away from the source. And finally, the direction of the field depends on charge polarity. It points outward for positive charges and inward for negative charges. Understanding these principles will help you analyze more complex electric phenomena in future lessons.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.